In this video, I'm going to introduce three ways of writing equations that have different purposes. Then we're going to talk about different types of reactions. We'll just scratch the surface. In a subsequent video, you'll learn more about different kinds of reactions that are out there, but today will be an introduction. Let's start out with a quiz, Ken. You stop the video, try and solve this, and I'll give you answers and tell you where to skip ahead if you got the answer right, and then I'll provide a solution for you to watch if you didn't. Go ahead and do this. Well, the answer you should have gotten is 2.82 grams of zinc nitrate. To solve this problem, we need first a balanced chemical equation, because this is basically a stoichiometry problem. So we're reacting zinc with nitric acid. Nitric acid is HNO3, and we're producing zinc nitrate. Zinc is 2 plus and nitrate's 1 minus, so there's that formula. And NO2, nitrogen dioxide, and H2O. Now this isn't balanced. I know that I need two nitrates, but I also know that I need nitrogen in more than one place. So instead of putting a 2 out here to balance the nitric acid, I'm going to start out by putting a 4, because I think that might work better. Now two of these NO3s are covered here. The other two find their home in the NO2 and the H2O. If I put a 2 in front of NO2, I balance the rest of my nitrogen, and it gives me 4 O's. If I put a 2 in front of the water, that covers my 4 hydrogens and gives me the other 2 oxygens I need. So there's my balanced chemical equation. Now let's do the stoichiometry problem. I want to find out the limiting reactant, so I'm going to start out with 1.05 grams of zinc. You could start out with the nitric acid. I'm just choosing this for some reason. And I want to find out how much nitric acid does it take to react with that. Well, here's what I know. Zinc is 65.39 grams per mole, so I'll use that to convert to moles. Once I'm in moles, then I can begin to do stoichiometry. The mole ratio is, according to the balanced chemical equation, 1 mole of zinc for every 4 moles of nitric acid. So now I've canceled away moles of zinc, and I know how many moles of nitric acid react. But I'm not given moles, I'm given milliliters. So I'm going to convert to grams and then use density to convert to milliliters. The molar mass of nitric acid is 63.012 grams per mole. So that allows me to get grams, and the density is 1.503 grams per milliliter. So that allows me to get milliliters. Once I do my calculation, I get 2.69 milliliters of HNO3. But the problem tells me that I only have 2.5 milliliters, and so I'm going to run out of HNO3. That means this is the limiting reactant for this problem. So to answer the final question, I need to start out with my 2.50 milliliters that are going to limit my reaction, and I'm going to convert that to the product that I'm interested in, which is the zinc nitrate. First of all, I know that 1.503 grams are going to be 1 milliliter, and so this will give me grams of HNO3. I also know that 63.012 grams per mole is the molar mass of nitric acid, and I know that every 4 moles of nitric acid will produce 1 mole of zinc nitrate. So with these calculations, I've now converted to moles of zinc nitrate. I want grams of zinc nitrate, so there's only one other step, and that is to use molar mass. The molar mass of zinc nitrate is 189.398 grams per mole. Moles are now canceled out, and I will have grams of zinc nitrate. The answer to 3 significant figures is 2.82 grams of zinc nitrate. The first type of equation we're going to look at is called a molecular equation. This is the type we're the most used to. We write them all the time, and these use complete formulae for all reactants and products. So this doesn't indicate the presence of ions. Here's an example. For the reaction of lead nitrate and potassium iodide, this is what I'd write down for a molecular equation. PbNO3, 2, and I'd indicate that that's aqueous, and 2 potassium iodide, 2Ki, also indicate that that's aqueous. Complete molecular formula creates two KNO3s, also aqueous, and I'm going to have solid PbI2. So I've got a complete formula for both reactants and for both products. The next type of equation is called an ionic equation. An ionic equation gives us a little bit more information about what's really going on in the reaction. It shows the formula of soluble strong electrolytes. So anything that would normally be as ions in the solution, we show them in the equation as ions. When these are balanced, you have to show balance not only of matter, but also of charge. So this is the molecular equation for the reaction that we were just talking about before. Here's what the ionic equation would look like. Lead nitrate is an aqueous soluble solid. So in solution, that means it would mostly be ions, and so that's what I'm going to write down. I'm going to split up Pb2 plus and nitrate. Now notice I'm putting two nitrates because that subscript tells me that when this compound really does dissociate in water, I'm going to have two nitrates for every lead. Ki is also aqueous, so I'm going to write that down. 2 K pluses and 2 I minuses. On the other side of the arrow, I have potassium nitrate, which is also aqueous. So there would be 2 K pluses and 2 NO3 minuses. And PbI2 is not soluble. It's a solid. So I can't split it up, because in solution it wouldn't be split up. It would be a solid mass laying at the bottom. Now, if you look at this equation, one thing you'll notice is there are some things that really aren't undergoing any change at all. Well, we have an equation that kind of gets rid of those and gives us a shorthand version of what's really going on. And those are called net ionic equations. Net ionic equations show only the ions that actually undergo chemical change, and they ignore what we call spectator ions. So here's the ionic equation for the reaction that we were just working with in the last example. If you look at this equation, you can see some things that on the left-hand side of the arrow and the right-hand side of the arrow are identical. 2 nitrates, nothing happened there. It's 2 nitrates before and after the reaction. 2 potassium ions, same deal. It's the same stuff before and after the reaction. So if I take the spectator ions out, those are what we call spectators, because they're there but they're not participating, kind of like if you're a spectator at a football game or something like that. When we take the spectators out, we have the net ionic equation, which amounts to this. Pb2 plus 2I minus makes PbI2. That net ionic reaction gives us some insight into what's really happening in this reaction. There are a lot of species there, but some of them really aren't undergoing any chemical change. Next, we're going to look at a few types of reactions and start to get reacquainted with how we can predict the products of reactions if we only know what the reactants are. The first one we're going to look at is acid-base neutralization. When an acid reacts with a base, you have predictable products, and they're going to produce water and a salt. Now, there are some instances where the definition of acid and base can be expanded so that the water doesn't actually even have to be there. But most of the time, that's what we're going to see. Here would be an example. Let's say I was reacting nitric acid, HNO3, aqueous solution, and potassium hydroxide, KOH, also an aqueous solution. Well, this is an acid. You can identify acids, remember, because they start with H. And this is a base. Ionic bases end in OH. It's going to produce water and a salt. It's often helpful to write the water as HOH, but you certainly don't have to. This isn't aqueous. This is just a molecule. It's the water that everything's dissolved in, actually. And then the salt is potassium together with nitrate. Remember, the salt is the cation from the base and the anion from the acid. So potassium's 1 plus, nitrate's 1 minus, so KNO3. And this turns out to be aqueous. We'll refresh our memory of the rules later on. It's already balanced the way it's written. So that's the molecular equation for this reaction. Let's write an ionic equation. Nitric acid is a strong acid. Strong acids can be split up because they're strong electrolytes. So I'll split it up to H plus and NO3 minus. Potassium hydroxide is a soluble salt. It's aqueous, it says, so I can split that up to K plus NOH minus. Water, I can't split up. It's not an electrolyte. Potassium nitrate is aqueous, and that is an electrolyte. So K plus and NO3 minus appear as separate species because that's how they are in solution. So that's the ionic equation. Now if I wanted to write the net ionic equation, I have two spectators that I can remove. Nitrate's one, potassium ion is the other one. And so here's the net ionic equation. H plus OH minus is HOH. Water is made from protons and hydroxide ions. That's a very common net ionic reaction for acid-base reactions. Another place where acid-base reactions show up where it doesn't seem like they should is when you have a salt that reacts with a base. And there are some salts that are able to release H plus ions on their own and then go on to neutralize more base. These are called acid salts. Acid salts you can identify because their anion starts with H. These are ionic compounds that have the anion like HSO4, 1 minus, or HCO3, 1 minus, or H2PO4, 1 minus. These are all acid salts. When you see those anions as part of a salt, then you know that that salt can itself function as an acid. So here's an example of what I'm talking about. Let's say I had NaHSO4, and this is reacting with potassium hydroxide, which is a base. This looks like a salt reacting with another salt, and so you don't think of this maybe at first as an acid-base reaction, but it is, because HSO4 1 minus is actually an acid salt. That anion is an acid. It can release this H and neutralize some base. So it's going to do that, and I'm going to get H2O or HOH, and then I'll get some Na2SO4s and some K2SO4s as products as well. So two salts here because I have two cations to deal with. You won't see that a whole lot, but you will once in a while. When you're writing an ionic equation or even a net ionic equation for weak electrolytes, those weak electrolytes still have to be written in their molecular form. Now this goes for insoluble salts, but it also goes for weak acids and weak bases. Like here's an example of a weak acid reacting with a strong base. Here's the molecular equation, but when I go to write the ionic equation, I can't split up this acid because it's not one of my 6 strong acids. So I have to still write the ionic equation with this together as HC2H3O2. Sodium hydroxide I can split up because that's aqueous and it's soluble, it's a salt. So Na plus OH minus. And then on the right hand side of the arrow, that's aqueous and it's a salt, soluble. So Na plus C2H3O2 minus plus H2O. Well, I can't split that up because it's not a strong electrolyte, it's just water. If I'm going to write the net ionic equation, I can take sodium out of here, but I still have to keep that weak acid together. So it's C2H3O2, NOH minus makes acetate ion and water. Same thing is true for a weak base reacting with a strong acid. Ammonia is a weak molecular base, and HCl is a strong acid. I left the water out of this, but I could have placed H3O plus over here and then H2O over here, so water and a salt gets produced. But I'm simplifying this, and I'm just going to leave that stuff out of there and write this. So it's strong acid plus weak base just makes the salt. Alright, so if I'm writing the ionic equation, how can I write this? I can split up H plus and Cl minus because HCl is a strong electrolyte, it's a strong acid. But I cannot do anything like that with ammonia. Over here I've got an aqueous salt made of the ammonium ion, which is NH4 plus, and the chloride ion. Spectator, chloride. So the net ionic equation is H plus NH3 makes NH4 plus. Notice that NH3 never gets split up or written in ions in any way because it's not a strong electrolyte. Even insoluble hydroxides or oxides can react with acids, and the acids drive the reaction forward and make it soluble by reacting with it. Here's an example. If I'm reacting magnesium hydroxide, which doesn't dissolve in water but has the form of a base, with a strong acid like HCl, the reaction will proceed to produce water and a salt. So HOH, and I'll need 2 of them, and the salt. And the salt is going to be magnesium chloride. Magnesium chloride is an aqueous solution. I happen to know that. After we learn a few rules, you will too. And so if I was going to write the ionic equation for this, I still can't split up MgOH2 because it doesn't dissolve. But I can split up the strong acid to H plus and Cl minuses. Can't split up water, so that's just 2 HOH. But I can split up magnesium chloride because that's a salt that's aqueous, so Mg2 plus and 2 Cl minuses. I do have a spectator. 2 chloride ions I can net out of there. So the net ionic equation is MgOH2 plus 2H plus gives 2 water and a magnesium ion. Now it's your turn. Here's a molecular equation for when an insoluble oxide reacts with a strong acid. I want you to write the ionic equation and then the net ionic equation. Stop the video, try it yourself. I'll give you answers in a sec. Okay, here's the ionic equation. Al2O3 I cannot split up. That's an insoluble solid, so I have to keep it as Al2O3. HCl is a strong acid, which makes it a strong electrolyte, so I can split that up. That gives me 6 H pluses and 6 Cl minuses. On the other side of the arrow, AlCl3 is a soluble salt, so I'll split that up, and that gives me 2 Al3 pluses, because aluminum's 3 plus, and actually 6 Cl minuses. And then I have water, which I can't split up. I do have a spectator here. It's chloride, and so my net ionic equation is Al2O3, still can't split that up, plus 6H plus gives 2 Al3 plus and 3 waters. Next type of reaction we're going to look at, and this will be the last one for today, is precipitate forming reactions. A precipitate is a solid that forms in a solution when a chemical change takes place. These kinds of reactions are just reactions that produce insoluble products. Here would be an example. If I take cadmium nitrate and react it with sodium sulfide, sulfides typically are not soluble in water. And so this is what I'm going to end up with. Cadmium reacts with sulfur. It makes this cadmium sulfide 1:1, and that's going to be a solid. That thing is what we call a precipitate. And then I'm going to get a second product, and that's sodium nitrate, NaNO3, which turns out to be actually aqueous. Balancing requires that I put a 2 here. Now if I were to write the ionic equation for this, I could split up the cadmium nitrate. That'd be Cd2 plus and 2 NO3 minuses. I could split up the sodium sulfide. That would give me 2 Na pluses and an S2 minus ion. But I could not split up the precipitate. The cadmium sulfide is a solid, so that has to stay together. And I could split up the sodium nitrate, so 2 Na pluses and 2 nitrate ions. I do have spectators here. Nitrate and sodium are both spectators. So the net ionic equation would be cadmium 2 plus S2 minus gives me cadmium sulfide. That's really what's happening in this reaction. The only way you're going to know if precipitate will form is by knowing what your solubility rules are. So this is going to require a bit of memory. You have learned these solubility rules before, maybe in another chemistry class, but we'll go through these and review them. If you're not familiar with them, reacquaint yourself with them. First of all salts of the alkali metals, which means the group 1s, are soluble. So we're talking about Na plus, Li plus, Rb plus, K plus. Any salt that has those as their cation is going to be soluble, no exceptions to that rule. There's another rule. All salts who have the cation ammonium, NH4 plus, or have the anion nitrate or chlorate will be soluble. And almost all the time, C2H3O2 salts, acetate salts, are also soluble. Now there is one exception, and that is this. Silver acetate isn't really soluble. It's only slightly soluble. But otherwise, all acetates, ammonium salts, nitrate salts, and chlorate salts are soluble. All salts whose anion is chloride, bromide, or iodide. Salts that have that are called the lower halides because they're halogens, but they're the lower ones on the chart. The upper one doesn't fit into this rule, fluoride. Lower halogen ions are soluble, except the ones that are made with silver, lead-2, or this weird polyatomic ion called mercury-1, Hg22+. Those things would be insoluble, but all the other salts that contain those anions would be soluble. Another solubility rule: every salt containing sulfate, SO42-, will be soluble, but there are some exceptions. Lead-2, calcium, strontium, barium, so those are three things from column 2, and there's that mercury-1 ion again. If those are the cation, it's not soluble, but everything else is soluble if sulfate's the anion. Nearly all ionic compounds that contain hydroxide ion, that's OH-, or oxide ion, are insoluble, except those made with group 1 ions. Remember that sodium, potassium, rubidium, those group 1s, first column, and calcium, strontium, and barium. All ionic compounds that have phosphate ion, the carbonate ion, sulfite ion, or sulfide ion won't be soluble, except the things that we know are always soluble, which is ammonium, if that's the cation, or any of the group 1s, sodium, potassium, etc. If those are the cations, then they would be soluble. Otherwise, they're insoluble. So you can use these solubility rules to figure out, predict, if you're going to get a precipitate to form. Next time we're going to look at a few other classes of reactions, but in the meantime, become reacquainted with these solubility rules and sort of commit them to memory, especially the first few.